We're going to solve a second problem using the reduction of order method. What we're going to do is we're going to find a second solution to this differential equation, y double prime plus 9y equals 0, if we're given that the function y1 equals sine of 3x is a known solution. We're going to follow the same method as the last one. And so we start by assuming that the second solution, y2, has the form of y1, the known solution, times some unknown function u. So specifically for this example, we're assuming that y2 is equal to the sine of 3x times u, which is easier to write the other way, u times the sine of 3x. And then we can get y2 prime. Again, we have to use the product rule because we have a function u times another function sine of 3x. The derivative of the first function is u prime times the second function sine of 3x plus the first function u times the derivative of the second function sine of 3x. The derivative of sine 3x is going to be the cosine, the derivative of sine is cosine of 3x. And then using the chain rule, the derivative of 3x is going to give me a 3, which I'll put in the front. So we have the first derivative. Let's go ahead and get the second derivative, y2 double prime. Remember, when we get all the derivatives of y, we will substitute them into the original differential equation, and then we will solve for the unknown function u. y2 double prime. So if I use the product rule on the first term of y2 prime, the derivative of the first term, u prime, is going to be u double prime, times the second factor is sine of 3x, plus the first u prime times the derivative of the second factor, derivative of sine, is going to be 3 times the cosine of 3x. So that's the first term in y2 prime. For the second term, I'm going to apply the product rule again. The derivative of u is u prime. First function derivative times the second function times 3 times the cosine of 3x plus the first function u times the derivative of the second function. The derivative of cosine is going to be negative sine, and then from the chain rule I'm going to get another 3. So I'm going to get here a negative 9 sine 3x. That got a little bit squished. Okay, because the 3 times the 3 gives me the 9, and the derivative of cosine is negative sine. I can simplify, and the two middle terms I can combine. So I get u double prime sine of 3x plus, let's see, I have a 3 and a 3. So I get 6 times u prime cosine of 3x if I add those 3's together. And then I get a negative 9u sine of 3x. Now I need to plug the y2 and its derivatives into the original differential equation. So we're going to substitute y2 prime, y2 double prime into the dE. And we're going to get something like y2 double prime plus 9y2 equals 0. Plugging in y2 double prime, I get u double prime sine of 3x plus 6u prime cosine 3x minus 9u sine of 3x. That's all for the derivative y2 double prime. Plus 9 times y2. y2 is actually u times the sine of 3x, and that equals 0. So with reduction of order, what's going to always happen when you collect the terms involving u double prime, u prime, and u, the coefficient of u is always going to end up being 0. And so you'll notice here that there's two terms that involve u, this term and this term, and they're the same but opposites. So I get negative 9u sine 3x and positive 9u sine 3x. So those two terms are going to cancel out. So that's the part reduction of order. I'll show you specifically why in just a second. What's left is u double prime sine of 3x plus 6u prime cosine of 3x is equal to 0. I can actually make a substitution now, and I'll show you what that substitution is. Let me just leave the last line. Remember, I'm trying to solve for u. That's my unknown function. If I make the substitution, if I let w equal u prime, so w is a function, and then w prime will equal u double prime, into this differential equation, what I'm going to get is u double prime is w prime, so I get w prime times the sine of 3x plus u prime is w, so I get 6w cosine of 3x is equal to 0. What I've actually done is reduced my problem from working with a second order differential equation to a first order differential equation. Notice the highest order here is 1, so that's where the name reduction of order comes from. So what we can do, we can solve this differential equation. W is the unknown function that we're looking for. It's either first order linear or it's separable. I'm going to go ahead and solve it as a separable differential equation. So I'm going to get all the w's on one side and all the x's on the other. So I would get w prime sine of 3x is equal to negative 6w cosine of 3x. And if I divide by w, I'm going to get w prime over w equals, dividing both sides by sine of 3x, negative 6 cosine 3x divided by sine 3x. Now that I've separated, I can integrate both sides with respect to x. On the left, I'm going to get the natural log of the absolute value of w. On the right, if I make a u substitution, if you want to do this, let u equal sine of x, then the derivative of the bottom, which is sine, is going to be cosine of 3x times 3. So if on the top, I write this as 3 times the cosine of 3x, and on the bottom I have the sine of 3x, then the top is exactly the derivative of the bottom. And so it integrates to the natural log of what's in the bottom. So I get negative 2 natural log absolute value of sine of 3x plus a constant. So I can take the negative 2 and make it the exponent here. And so I can take both sides and raise them to the e power. So if I put e to both of these sides, what I'm going to end up with is absolute value of w equals e to the ln just gives me the sine. So that's sine of 3x to the negative 2. And then it's times this e to this constant. That's going to be another constant that I'll call k. Notice that this is going to be s squared, so I don't need to worry about the absolute values. So I'm ending up with actually the sine to the negative 1 is the cosecant. So I'm going to get the cosecant squared of 3x, taking care of this negative 1 power by making the sign its reciprocal. And that's going to be times e to the c, which is just a constant k. And I'm going to drop the absolute values on the w because that positive or negative sign can be absorbed into this k. Now remember, I'm actually not trying to solve for w. What I'm trying to solve for is u, so I do have one more step to go, which is to put back in that u prime is equal to w, and then I have to solve for u. And so what I'm going to do is integrate both sides with respect to x, and so I get u is actually equal to k. The integral of cosecant squared of 3x is going to be a negative 1/3 cotangent of 3x. And that I'm going to have to add another constant of integration. Let me call it c. So that's actually my solution. I can put the negative 1/3 and the k together and just make that a different constant. And so what u is going to be is some constant k1, if I put k and negative 1/3 together, times the cotangent of 3x plus c. And I just need something for u, so I'm going to pick something kind of simple. If I let k1 equal 1 and c equal 0, then what I get for u is simply the cotangent of 3x. And my second solution, y2, which is the first solution times u. Remember, y1 was the sine of 3x, and then u is just going to be the cotangent of 3x. And since cotangent is cosine over sine of 3x, this simplifies cosine over sine. The signs cancel to the cosine of 3x. So the two solutions are y1 is sine of 3x and y2 is the cosine of 3x. And the general solution then is c1 times y1, which is the sine of 3x, plus c2 times y2, which is the cosine of 3x, is the general solution to that differential equation.